Good evening once again. So today we want to be looking at introduction to inferential statistics. Now we have discussed descriptive statistics, then probability. So I already said before that the link is probability that link descriptive and inferential statistics. So let's talk about introduction before we go fully into inferential statistics. There are three kinds of lies: lies, damn lies, and statistics. This word of Disraeli, the former Prime Minister of UK. So if you don't do the right thing, you can be telling lie with statistics. You may tell lie unknowingly or knowingly. Unknowingly, if the person does not understand statistics, he will just say something, he will just bring result that is not valid. And of course, as long as it's not true, it's not the right thing, it's a lie. But that person has told lie unknowingly. In other words, some people can cook data, they manipulate data, and they come with statistics. Many of these people you quote, so and so, some of them is lie. But some of them cook statistics, they cook data. At the end of the day, they tell you something that is not valid. And that is why, for you not to tell lie, of course, you can decide not to tell lie, but for you not to tell lie unknowingly, you need to understand your statistics. So, and that is the most important aspect where people have this problem is this inferential statistics. So, before starting in discussing our inferential statistics, let's start with the concept of inference. Inferential. Inferential is from the word inference. I've talked about it before when we talked about the logic of scientific reasoning. Inference is a generalization made about a large group or population from the study of a sample of this population. You make a generalization about the population from what you find from the sample. You know, as you have said before, as a researcher, you are interested in what is happening in the population. But because of logistic reasons, most of the time you cannot attend to the whole population. You cannot collect data from the whole population. You take a sample, which is a subset of the population. So whatever you calculate, all the statistics you calculate, they are estimate of the parameter in the population. So the summary you will have calculated, you will have presented, if you have attended to all the elements in the population, it's called parameter. But when you take sample, the summary you get is called statistic. Without S, it's only when it is plural that you put the word S. It's different from statistic as a subject. Now, from that statistic, you make generalization, you give a glimpse of how the population parameter will be. That is what we call generalization or inference. And I already said before that this inference, there are two types: inductive inference and deductive inference. In inductive inference, we go from specific to general. We made observation, design pattern, and make a generalization after and infer an explanation. So here, you just most of the time, you do this, you make this inductive inference when you do a cross-sectional study. So cross-sectional study, then you can only make deductive inference when you are doing an analytical study. In a cross-sectional study, the best you can do is to generate hypotheses. For example, now, when you say you are doing pattern of driving in Abuja, so here you just gather your questionnaire, what you think, maybe from literature review, what you think are important and what you know that are important when it comes to driving. Talk about, do you have what is the age, what is the note the sex of the person, if the person have driver license, if the person attended driving school, and many other things. So those characteristics, and you also ask if the person has been involved in accident, how many times, at what age the person start driving. All those things are what you ask. So at the end of the day, when we finish the study, you may begin to link some of these with the maybe accident, for example. Is there any relationship between or association between age and accident? Maybe the younger one are more likely to have accident than the older one. Between sex and accident, maybe female or male are more likely to have accident than the other. You may talk about the age, if the person has license, maybe the person that doesn't have license are more likely to have accident. All those things, we need to look for association. Because it's a descriptive study, you make some generalization. You may say that, oh, so, among younger one are more likely to have accident than the older one. It's inductive inference because you are just generalizing. You are generalizing from you are generalizing from observation you have made. But that form of generalization is like you are trying to create hypothesis, create theory that, oh, there's association between this and this. It's not as if you started with that one in mind that, oh, there's an association between age and accident. Let me study it. If that's what you want to study, oh, there's a difference between the rate of accident in the rate of accident between younger and older one. That one is different. You didn't start with that. You just collected that, but after you have analyzed, you start look at the pattern. You are generating hypothesis. You are making inductive inference. Oh, there is an association between this and this. That's an inductive inference. Because whenever association you are talking, say, between this and this, you are talking of what is happening in population. Well, from the sample. Then, if somebody now say, oh, is it actually true? When maybe after you publish the work, and then maybe the work say that, oh, the rate of accident is higher among the younger age, you know, it's actually true. You can now conduct a study to test it. So that study that will test it will be an analytical study. In words, in that situation, you sample those younger ones, you sample older ones, and now begin to ask questions about accident rate among them. In that situation now, you have started with the hypothesis that is there any association? No, there's an association between accident and age. So by the time you finish, it may be true, it may be false. So your conclusion will say, oh, it's true, there is an association. It's not true, there is no association. So that is deductive inference. That's generalization you make when you test an hypothesis. After you have tested an hypothesis, generalization you make is deductive. But when you didn't test any hypothesis, but somehow, the generalization, try to create a theory or an hypothesis. In creating that type of generalization is called inductive inference. So let's move further. So for us to understand inferential statistics further, we need to understand the concept of sampling distribution. Can you see the word distribution keep on coming? The first time we talk about distribution generally, so we say it's pattern of occurrence of a values of a variable in a data set. Pattern of occurrence, that is, how many have this value, how many have this value. So if it's weight now, well, how many weigh 70, how many weigh 64, how many weigh, you begin to put the frequency. You're going to see some that value, more of the people have it, some they don't have it. So that pattern of occurrence, the distribution, and we have already talked. You said that you call it frequency distribution, relative frequency distribution, cumulative frequency distribution, cumulative relative frequency distribution. We talked about that. We also talk about probability distribution, where we talk about distribution of the value, the probability of all the possible value of a random variable. That's probability distribution. So here we say that it's virtually the same. Here is sampling distribution. Here now, Instead of you looking at what is the pattern of occurrence of value of a variable, you take sample. When you take sample many times, you summarize. You know, when you summarize each sample, as I've said, you get a statistic. So the statistic, if you have summarized categorical variable, the statistic will be a percentage or proportion. But if you have summarized quantitative variable or numerical variable, you'll be talking of mean, mode, or median, standard deviation, variance. Those are the things you'll be talking about. That's what you get by summarizing numerical variable. Whichever way, any of them, whether it's categorical variable or whether we are talking about percentage or mean, mode, median, sensitivity, specificity, or standard deviation, whatever, anything you summarize from this. But when you take sample, you summarize it. You take another sample, you not get the same thing. You take another. So when you take many sample many times, this summary statistic may vary. Some of them will be the same, but you cannot expect it to be the same. You take sample 50 times now. The mean you'll be getting will not be the same, or percentage you are getting will not be the same. So if you say percentage of female, maybe now university now, or University of Abuja, say percentage of female in the, and somebody takes sample of 100 or 100 people per time and calculate how many female there. You get, maybe you get 51%. You take another, you may get 55. You take another, you may get 49. You take many times. As you are taking many times, it gives you different value. Some of them may be the same. Maybe it is a bet. The issue is that taking sample many times, the statistics you get different. So the pattern of occurrence of those statistics you get through taking sampling many times is called sampling distribution. And if the statistic you are looking at is mean, the mean, you calculate the mean age of student, you take sample of starting number, maybe 200 or 50, you calculate their mean age for that graduate student, you may say, oh, the mean age 22. You take another one, 19. You take another one, 23. You may get 19 again, 20 again. You take as many. So you go to have different value. The pattern of occurrence, each of them, how many times do we have 20 as me? How many times we have 19 as me? How many times we have 22 as me? Something like that. That is sampling distribution. Now, what is the implication of that? When you take sample many times, you calculate the statistic. It will give you different things, as I've told you. We call it sampling variation. Sampling variation. Now, when you have the sampling variation, now, this sampling variation, if you now try to calculate the mean of this sampling variation, if it is percentage you have summarized, that is for categorical variable, you have many values, you calculate the average. It gives you a value, which is the mean of the sampling distribution. Now, if it is quantitative variable you are dealing with, you calculate the mean, the average. You now calculate the average of the average, which is the mean of the mean. This mean of the mean, whether it's for categorical or for numerical variable, is believed to be the parameter in the population. The parameter. Let me give an illustration with this. There's an illustration here. Let's assume that we have many samples. Look at the population. Look at this diagram. This big circle is the population. And each circle you see inside the circle is the family, one family. And we are talking about maybe number of children in each family. So if you take, this person has taken sample 9 times from that big one. Population takes sample of four families to calculate the average number of children in the family. So you see, this one has 3, this one has 2, 4, 1, 2, 3, 3, 4, 5, 2. If you look at it now, you can plot it. That is what they plot. Out of the 9, how many have 3? How many has 1? It's only 1 that has 1 as the mean. How many have 2? It's 2 that have 2 as mean. How many have 3? It's 3 of them that have. How many have 4? It's 2 of them. How many have 5? It's 1 of them. So now you can actually, if you look at the different mean, 9 mean, If you now calculate the average of that 9 different mean, you add it together, calculate that, it gives you 3. And you look at the mean in the population is 3. The mean number of children, mean you can see is 3. But when they take sample, it gives you different value. When you now add all the mean of the 9 means from the 9 sample together and divide by 9, it gives you 3, which is, can you see now, the mean of the sample, the average or the mean of the sampling distribution is regarded to be equal to the parameter. So if it is categorical variable you are looking at, if you take sample many times and you calculate the percentage, different percentage, if you add all the percentage together and divide by the number of samples you take, it is believed that percentage you now get will be the real value, which is parameter. You know, the real thing you want to know in the population is called parameter. So it can be percentage, it can be mean, it can be anything. So if you now summarize the, you calculate the average of the mean you have gotten, yes, of the statistic you have gotten, calculate the average. It is believed that it is equal to the parameter. Now, because there are different values now, you can calculate the mean. If you can calculate the mean, you can as well calculate the standard deviation. If you calculate the standard deviation of sampling distribution is called standard error. Standard deviation of sampling distribution is known as standard error. Some people, when you see, you ask them, what is standard error? They say population standard deviation. It's not true. The standard error is the standard deviation of sampling distribution, but it is believed it should be equal to the standard deviation in the population. That's why some people now say erroneously is this population standard deviation. It just believes that it should be equal to the population standard deviation. So standard error is not population standard deviation. It's just by proxy that they should be equal to the standard deviation in the population. Standard error is a standard deviation of sampling distribution. Now, if you ask me, so what is the essence? Okay, before I explain that, nobody actually will need to think. Nobody now take sample many times and say they want to calculate standard error. Over the year, they were doing it before, in those days. The intelligent people now discover that if you calculate standard error, if you know standard deviation of the population and divide by the square root of sample size, standard deviation divided by the square root of sample size is give you standard error. You don't need to calculate standard deviation once, one sample, divided by the square root of sample size, give you the standard. From here now, you now know there's a relationship between the sample size and the standard error. Is inversely proportional. That is, if the sample size is very high, the standard error will be low. And the standard error, you know, we say is the standard deviation of the population. Standard deviation is measure of variability as spread the value of the data set is. So if there's small standard error, it means that it's not widespread. The values are close. So now the standard error will be reduced if you can jack up the sample size. But if you reduce the sample size, the standard error will be high. So standard error, how do you interpret? If you say standard error is high or low, it's relative, unless you compare two standard error. So when we say standard error is high, what is the implication? When standard error is high, it may mean two things. It may mean that the attribute in the population, they are wide apart. For example, that if you compare height and weight, the standard error of height and weight is higher than that of height. The standard error of weight is higher because weight vary more than height in the population. Height vary less. So if the standard error is big, it may mean that, oh, that attribute vary a lot, differ among people. Now, it may also mean that your estimate is too far from the population parameter. You know that you take some